I'm Colin, the trainee of this project.
My name is Tien. I'm the trainer in this project.
I'm Darren and I'm responsible for the control setup.
This project attempts to plan an effective training program for single-leg squat skill acquisition. This video serves as an introduction to the project's metrics, justifications, and details, while introducing skill criteria for single-leg squat. So to take the measurement, we have two GoPros, one in the sagittal axis and one in the coronal axis, and then we have the tripods that are 0.9 meters tall, and both of them are 1.8 meters away from the subject. In case you're wondering, here's a force plate that we didn't get to use, so don't worry about it. We used a 1 meter long ruler as well as tape on the participant's body as dartfish references. This is how it looks in action.
First, we map the single leg squat onto 4 skill movement criteria: adaptability, accuracy, efficiency, and consistency. For task performance, we select squat depth measure by knee flexion, which is a gold standard, and it reflects the overall task demand placed on the system. For movement quality, we focus on frontal plane control using FPPA, which can indicate knee valgus varus or neutral alignment. And FPPA is sensitive to increasing task demand. For movement strategy, individuals may adopt different combinations, making it hard to standardize and measure. Finally, for consistency, we use variability of knee FPPA, which reflects the stability or movement execution. From this criteria, we derive one outcome measure and two process measures. The outcome measure is knee flexion, where greater knee flexion indicates higher task demand. The first process measure is the FPPA, which reflects frontal plane movement quality, and the values closer to 0 indicate better alignment and control. The second process measure is hip FPPA, which provides insight into how the hip contributes to frontal plane control.
So we acquire our baseline data through 5 repeated squat trials. To ensure reliability, every trial was strictly standardized. Participants stood barefoot on a force plate with their arms crossed securely over their chest. Next, we process the video recordings using Dartfish. By pausing at the time frame of maximum knee descent, we map key anatomical landmarks to extract the wall interior joint angles. We then mathematically synthesized and calculated these values into quantitative baselines. We converted the wall sagittal angles into true knee flexion angles and calculated the dynamic hip and knee frontal plane position angles mean change by subtracting the value from initial standing from maximal knee descent. Finally, our data allows for a clear comparison against the control across all 3 measures. While the control achieves superior depth, they demonstrate a superior waist side valgus deviation. In contrast, our trainee maintains excellent proximal hip symmetry, yet struggle with distal knee alignment, and this isolates their primary movement fault strictly to the knee and ankle, providing a precise localized target for our training plan.